Okay, good afternoon, students. Let us start today's discussion. In the last from the since last few lectures, we have been discussing about the FETs, field effect transistors, and that was junction field effect transistor, a type of field effect transistor in which we have the junction at the gate, PN junction kind of thing, which has been reverse biased, and by the applied at gate PN junction, we were able to control the channel through which the current flows. Okay. So when there was no reverse biasing applied at the gate in the form of the BGS, we had the largest current, whereas when we applied and gate potential, so that the PN junction at the gate reverse biases, then the current decreases. And there are different things which we have seen qualitatively, and also in the last lecture we tried to have quantifying the characteristic of the JFET. Uh, Before proceeding about the circuits, let us discuss another FET here, which is commonly called as MOSFET or metal oxide semiconductor field effect transistors. So these are essentially metal oxide semiconductor stack to form a special structure there, which is in short is called as MOS or metal oxide semiconductor. So we have two types of MOSFETs. One is called as depletion type of MOSFET, another is called as enhancement type of MOSFET. So we will look at both of these. So first here, let us understand the depletion type of MOSFET. So the cross-sectional view of the depletion type of MOSFET is shown in the figure here. So this depletion type of MOSFET is no different than the junction FETs which we have just studied. Here also we have an inbuilt channel here. Okay, so channel is already there, which connects two regions and of the same type called as source and drain. Okay, so this is just the cross-sectional view here. Okay, so let us try to understand what actually we are having here. In the metal oxide semiconductor field effect transistor, the essential part is the so-called as MOS structure, metal oxide semiconductor structure. This. Okay. In this structure, we can control the so-called channel here in the semiconductor region with a applied gate voltage. There is some application of the voltage at the top of the metal, that is called as gate, and the semiconductor can also be connected with a potential or mostly with ground here, and this is called as substrate. Okay, so here already the channel is there, we here have two more regions so that we can control okay. So we have two more regions on either side here of the same type as that of the channel region is made of. Suppose this is N type here, then this is also going to be N type, and this is also going to be of the N type here. One is called as source and another is called as drain. Okay. So source and drain, just nomenclature, let us understand for now. We will try to see more about this as we discuss in this course. Okay, so this is not hanging like this here. This is actually put everything on a substrate like this here. Substrate is mostly made of the P type. Okay, so substrate is actually a part of the substrate was here. So this substrate is actually extended all over here. This in this region. Okay, so substrate is of opposite type. Say P substrate. On the P substrate, we make N channel device, and on N substrate, we make P channel devices. Okay, so that's what uh, is the convention here. So this is just the cross-sectional view here. Now, here in the depletion type of such a MOSFET here, already the channel is there. Okay, so channel is inbuilt. So we need to apply only a biasing voltage across drain and source. Okay, this we call this as a BDS, the potential between the drain and source, which will establish an electric field. Okay, if we apply such kind of voltage source across drain and source, then the drain is going to be positively at higher potential and source is going to be at lower potential. So what we see? We see a kind of electric field to exist between drain and source with the shown direction. So the electric field is actually from drain side to source side because drain is at positive potential as compared to the source. Okay. So because of this, the charge carriers which are there inside the channel, they will feel a force in the opposite direction to the electric field, and they will start moving from source to the drain, and the difference direction of the current is to that opposite to that of the electron flow. So the current difference direction is from drain to source like this. Okay, so that's how the current can be established to flow between drain and source. There is no problem in such a device because channel is already there. We don't need to induce the channel here. Okay, but we can modulate this channel. How we can modulate this channel? By applying a suitable gate voltage. Actually, this course doesn't allows much to discuss about the physical point of view of this, what is happening inside. But let us see what little bit of this to have qualitative understanding at least what is happening here. So metal oxide semiconductor, this is the main thing. We want to modulate this. Once the channel is there, okay, suppose this channel is there in this semiconductor, channel is always going to be in this semiconductor. Okay, it is not going to exist in the oxide or metal. Okay, so oxide is insulator here. So semiconductor is the right material where the channel is going to be exist here. So in this here, if we apply some suitable this potential across this structure between gate and substrate, then we can make the channel to change. Okay, how we can let us try to understand how this is happening here. Suppose this is BGB. Okay, B is for the substrate here, or body. B stands for body or substrate. Okay, so if we apply BGB between this, then suppose this kind of polarity we are applying. So battery of this is connected to the gate. It means it is supplying some positive charge here. Okay. So for overall neutrality of this structure, we must have supplied equal and opposite number of electrons here because of something called as capacitive coupling. Okay. Let us see what we mean by this capacitive coupling here. The gate is having it has been called here metal. Okay, as already we seen that the full form of MOS has been metal oxide semiconductor. Okay, so M stands for metal, but it is not necessary that it is made of the metal here, some metal. Of course, we can use metals like aluminum, or we can use, say, uh, silver or gold. Some materials can be used. We don't want a material which is uh, active in nature. We need a material which is inactive, okay, or noble in nature. So that kind of material may be prepared to be used as gate material, okay, so that its property is not going to change with time. So that okay, so that is the quality of this, but mostly this is not metal. Okay, in the uh, widely used transistors, uh, the gate is not made of metal really. This is made of polysilicon. Mostly polysilicon has been used for gate. Okay, so heavily doped. Okay, heavily doped polysilicon, but this is conductive in nature. Okay, anyway, either we use metal or this heavily doped polysilicon. This heavily doped polysilicon is quite cheap. Okay, that's why it has been used. So it is having metal-like characteristic. Thus, below the semiconductor uh, can be seen to in here. Okay, is separated by oxide here. Okay, the gate and substrate are separated by an oxide here. Oxide is insulating in nature. Okay, that doesn't allow the current to flow through it. So semiconductor uh, is not a really conductor, but near about this, okay, interface. Already we have here, say, doped N type here. So this region is more conductive, and we see here that electrons are there, and as we apply gate voltage, and gate voltage not changing to by a rapidly, say, okay, then what happens with the application of the gate voltage? We can say that there this establishes a kind of electric field between gate and body like this because of this potential difference. And due to say yes, in the semiconductor physics we have understood a little bit that due to thermal agitation there is generation of electron hole pairs. Okay, so because of now this electric field which we are showing here, the electrons which generate due to the thermal agitation will start moving in the opposite direction to this electric field. Okay, but these electrons don't reach to the gate here because the gate is insulated by oxide here. Okay, in between we have oxide insulator. So these electrons don't really reach the gate, but they get stuck at this boundary. Okay, so which is the boundary? And the boundary is oxide and semiconductor. Okay, so oxide and semiconductor boundary. At this boundary, these electrons get trapped here. So the number of electrons which get accumulated here is of the equal amount as that we have put a positive charge on the gate. So a kind of things happen here that if we make a change of in the charge at the gate by delta Q, equal and opposite change happens to uh, uh, okay at this oxide semiconductor interface, and these two charges are separated by the oxide thickness. Okay, so oxide is say this thick here. Okay, T ox here. So we can say that it is something like this. There are two conductive plates. On one plate we make a change in the charge by plus say delta Q. Then there happens to uh, take place a change in the charge by minus delta Q. Okay, so whenever we have this kind of nature, and this is happening because of change in the potential by delta B here. Okay, so delta Q, delta V, so we see a change in the charge, okay, due to change in the voltage, and this is nothing but called as C. Okay, dq by dV is equal to C, capacitance. So this is something like a parallel plate capacitor. This gate, okay, metal oxide semiconductor combination at the uh, gate here. This actually works as a parallel plate capacitor. Okay, so its value can also be given as in the terms of the parallel plate capacitor here. The capacitance value can be given as epsilon oxide multiplied by the area of this plate divided by TOX. Okay, we can also define something called as C by A, the capacitance per unit area to be given by epsilon ox upon TOX. This particular value has been traditionally called as COX is equal to epsilon ox upon TOX. Okay. So because of this capacity effect, we can try to understand. If we make a, if we put a positive charge on the gate, then equal and opposite negative charge is going to appear on the in the semiconductor at this semiconductor and insulator interface. On the other way, if we say that if we are putting say negative charge on the gate, then it is the positive charge which will appear in the semiconductor at the interface. Okay, so that is very important for us to understand the basic working here. Okay, so here let us come back and try to understand here our this is, this metal oxide semiconductor which just we discussed is here. This is metal, and here this strapped thing is oxide, and this below thing is full semiconductor substrate. In the semiconductor substrate we have the inbuilt channel. Okay, so channel is there. So if we put a positive gate voltage, then electrons are going to appear in the channel. On the other terms, if we put a negative charge on the gate, then positive charge is going to appear at the interface. Okay, so that's what we have to understand here for this case. So for n channel here, if we are putting the first say positive charge, then already the n type of channel is there. More electrons are coming into this, so more stronger the channel will become, and we will see a rise in the current if we have the same BDS to be applied. So across this drain and source, we may apply a voltage BDS, okay, to make it conduct. Let us first see what is here. On the other hand, if we apply a negative voltage, okay, negative voltage on the gate, then it is giving a negative charge on the gate, and equal and opposite positive charge will appear here. So this positive charge is going to uh, come from the substrate and will try to, positive charge is what? This is nothing but the holes. Okay, so holes are coming from the substrate, and in the channel electrons are there, a large amount of electrons are there. So few of these electrons are going to recombine with the holes. So in the process what will happen, that the electrons in the channel will be lesser because few electrons recombine with the holes. Okay, so the channel strength will decrease, means the electrons or the carriers present in the channel are going to decrease. So that will decrease the current. If we keep on actually increasing this negative potential more and more, then the channel will become weaker and weaker, and there may exist some negative gate voltage for which the channel may vanish. That may be called as the threshold voltage of this depletion type of MOSFET. Are the it is something like BGS of the JFET. Okay, something like this, BGS of the junction field effect transistor. So if we want to make the current zero, then it can be done. Whereas if we apply a other voltage, okay, other voltage greater than this BGS off, then the channel will be there and current will flow. So in this case, what we see, if we try to look at the characteristic here, ID and BDS, okay, suppose for a given BDS, we are trying to see the characteristic here. Sorry, for a given gate voltage. Suppose initially we didn't applied any gate voltage, that is BGS is equal to 0. Then channel is there, and if we change the BDS, then the initially the current is going to increase actually slowly, because the field, okay, electric field, due to this BDS across drain and source, okay, that will increase, and the current will also increase. That is a qualitative understanding here. So current is going to increase as BDS is increased, and for a particular BDS, what happens? There is no more change in the current. Okay, so the current becomes almost saturated for a particular value of the uh, gate voltage. Sorry, a particular value of the BDS voltage. Okay. So this is for BGS is equal to say 0. If we apply a positive voltage more than this, what we expect? A larger current to flow. On the other hand, this is BGS 1 greater than this 0, BGS 0. If we apply a lesser voltage BGS than 0, that is -1, -2, -3 volt, then our current will be smaller because channel strength has decreased. So say let us, this is for BGS is equal to -1 volt. Say BGS is equal to for -2 volts, something like that. And as we decrease the BGS and make it almost equal to this BGS off, okay, of the JFET kind of thing, then there will be no channel at all, and whatever the value of BDS we apply, current will not flow. Okay, so something like this we can understand, and the working of this depletion type of MOSFET. So this you can see here in this picture clearly. For BGS is equal to 0 volt, we have some value of the drain current. If we have a positive gate voltage, then larger current is seen. And for lower values of gate voltage, the current decrease, and there exists a corresponding value similar to the BGS of JFET, being called here pinch of voltage again, for which the channel vanishes and there is no current. So this is the output characteristic here. This is output characteristic. We can also have the transfer characteristic here. We have understood so far that transfer characteristic relates the output quantity with the input quantity. So input quantity is here the gate voltage, and output quantity is the current, drain current. So a graph which relates the drain current with the BGS, that we call as a transfer characteristic here, and shown over here. So the different scenarios, okay, for BGS 0, we have the maximum current here, IDSS, similar to the JFET, okay, IDSS, there is some nominal value. If we applied a larger gate voltage, say 1 volt here, for 1 volt here, the current is seen to be this much. Whereas if we apply a lower gate voltage, okay, say -1 volt, then there is some other current here corresponding to this, or even other voltages here. We have some other values of the current here, like this here. Okay. So we can see here that and if we decrease the gate voltage more and more, then at pinch of voltage the current becomes zero. So this gives a very nice transfer characteristics. So it is showing two kind of things. One in the one characteristic, okay, beyond the this vertical axis, on the left of this vertical axis, we see the current to decrease as gate voltage is increased in negative direction. This is due to the depletion of the channel, already inbuilt channel, and hence called as depletion mode. Whereas the characteristic on the right side of the vertical axis shows the positive values of the gate voltage. We have seen as we apply positive gate voltage, then electrons get enhanced in the channel, more electrons appear, and this is called as enhancement mode. So depletion type of MOSFET can operate in two modes. One is depletion mode and one is enhancement mode. So for N channel, this is true only for N channel, this discussion. We need to apply a negative gate voltage to operate in depletion mode and positive gate voltage to operate in enhancement mode. On the other hand, if we have a P channel, then what we will do? For P channel, the opposite thing will happen. Suppose we have here a P channel. Let us see quickly. For P channel, we start with N substrate. We have source and drain of opposite type, P regions, and a gate here, metal oxide and semiconductor. Now here we have the channel also say built and is of the P type. Okay. So this is here. The case source and drain. Now if we apply a positive gate voltage, now means we are putting some positive charge on the gate, equal and opposite negative charge will try to appear here, which is being supplied from the electron hole pair generated due to the thermal agitation. Okay, that is the only process by which it is getting generated here. So these now in this case, what we see, the vertical field. Okay, if we'll see, the vertical field is still of this. So electrons are getting attracted toward this again, but because now the inbuilt channel is of the P type, so these electrons are going to recombine with the holes here. Okay, recombination happens here, and due to this recombination, the channel carriers decrease. Due to recombination, channel carriers decrease. Okay, so due to this, what will happen? Now, if suppose we had connected some voltage difference across drain and source with the help of VDS, which had established some electric field between drain and source. So then this would have resulted in some current. Now as we have applied BGS, because of that a new thing has happened and channel current reduces. So what will happen to the current? Current is going to also reduce. Okay, current will reduce. So in the N channel, with the application of positive gate voltage, we have seen the channel to enhance. But for the P channel, we see the opposite to happen here. Whereas if suppose we apply a positive negative gate voltage, okay, then what will happen? The electric field will change its direction, and now holes will be attracted toward the channels and will enhance the whole construction. Whole construction will be enhanced. Okay. So due to this here, the whole construction in the channel will enhance, and that will increase the current. So just opposite is happening as well. It was happening for the N channel. So that's the basic difference between this. So if we again draw the output characteristic here between ID and BDS for say BGS is equal to 0. First, let us look at some current is there. Initially, the current is going to increase linearly almost, and later it almost flattens. Okay, it gets saturated. There is no further improvement, even though we increase the BDS. Now, if now currently we just saw that if we apply positive gate voltage now, due to that the channel was reducing and current was reducing. Okay, so if we apply a positive gate voltage, then current is going to decrease. So current will decrease like this here for a positive gate voltage. Suppose we apply a further positive gate voltage, then this current is further going to decrease, and so on, and there will exist a say gate voltage for which the channel will vanish and there is no current possible. On the other hand, if we apply a negative gate voltage, then channel get enhanced and the current will increase, something like this. So we have such a such different uh, output currents, okay, like this. So this is also going to work in two different modes, that is uh, sorry, if we try to plot the ID BGS curve, okay, transfer characteristic, then for positive values we see the current to decrease, and for negative values the current is going to increase. So something like this it will happen, okay, like this. So this is +1, +2, +3 kind of thing here, and here on this side -1, -2, -3 here. Okay, so just reverse thing we can see here. This is enhancement of the channel, and here in this we have depletion of the channel. Okay, so these things we can see for the P channel MOSFET. This is for P channel MOSFET. So For this depletion type of MOSFET, we can see that it is almost working with similar to the JFET here. So for BGS is equal to 0, we have ID is equal to almost IDSS here, the maximum current, nominal current here. And when less than BGS 0 volt, then we have this I drain current also to decrease. Okay. So same equation we can use as we have used for JFETs for the voltages less than 0 volt. Okay, BGS less than 0 volt equal to the BP for this N channel, and for BGS greater than 0 volt for the P channel, as already we have seen. And the type of MOSFET which we can see, this is for the P channel. Okay, so P channel already we have discussed that it is just having a different nature. For positive gate voltage, the current is decreasing, and for negative gate voltage, the current is increasing. Here we have the symbols for used for the depletion type of MOSFETs. So in the depletion type of MOSFET, already the channel is there. Okay, so for the channel, we just show this connecting line, joining line. Okay, one side is drain and this is a source, and gate is in between. We have seen that gate is separated with the substrate or channel side with the oxide here, metal oxide semiconductor. Okay, so because of this BCS gap between gate and channel, this gap. Okay, so this gap is here due to this oxide here, and drain and source are connected together, and we show a substrate also between substrate and channel. We can see that a PN junction happens to exist here. Okay, so this PN junction is just shown here by an arrow here. So this is for P channel here. Okay, for P channel, this PN junction is having this orientation. So this orientation is shown here for the P channel, and similarly for N channel, we have this orientation of the PN junction. So for that reason, it is shown over here. So this top diagram, both N channel, P channel, shows the nominal symbol here, standard symbol. Below is here showing that substrate and source both are connected together. So in both the N channel or P channel, the source and substrate are connected together, mostly to avoid a very prominent effect called as body bias effect. Okay, so this is very important effect. To avoid this, one tries to connect the source and substrate together. Okay, So just we can see quickly here that if we take the say n channel here for p substrate, we have n channel here, source, drain, and this is n channel. We have this gate oxide. Gate is made of the metal or polysilicon. Okay, so in this here, we can see that the source is also n type, drain is also n type, and channel is also n type. Okay, so actually we see everywhere, either in this region or here we see, or here we see, everywhere we see here this p-n junction to form. Okay, so everywhere we can see this under the source, under the channel, under the drain, this depletion region is there. Because of p-n junction. So p-n junction exists here. But we don't need a current to flow through this. Do we need a current to flow? No. We don't want a current to flow. Okay, so we either want these p-n junctions to be reverse bias, or either we don't bias it. Okay, so source actually is mostly referenced. Drain is at say higher potential, gate is also at higher potential. These actually, while in operation, we will see a more larger depletion regions to exist here under these regions, under the channel, under the drain. But under near the source, actually, we have something like this, because this is lowest potential. Okay, so if at most what we want, that we don't apply anything here. We can also reverse bias this, but we cannot forward bias this. The safest case could be like this, that we connect these source and substrate together to the minimum potential. If we don't do this, what will happen? This may substrate may have a say if it is having the higher value, then there is a chance that this source substrate p-n junction, okay, this may get forward bias. There is a chance, okay, that this particular uh, uh, p-n junction may get forward bias. Okay, we don't want that. On the other way, if we have the negative potential on this substrate here, then we have more reverse bias, and the something called as threshold voltage, that is controlled by the uh, something actually we haven't discussed over here, but something as a potential barrier between source and channel also. Okay, so that potential barrier is going to change here, or we can say that if we say apply a negative voltage at the substrate, then we will need a larger gate voltage to have the same amount of electron concentration in the channel. Okay, essentially there is a corresponding value of the gate voltage. Okay, to we need actually a larger gate voltage for doing the same job. So essentially we don't want this is not a good thing to happen. So to avoid this effect here, we actually connect the source and substrate together. This effect is going to be more prominent and more we can understand more physically when we discuss this enhancement type of MOSFET. Okay, but time is almost over. Okay, so we stop here. We will continue from with our discussions in the coming lecture. So for now, you should study about up to at least this different type of MOSFET and try to explore the concept of this. We have very rapidly gone through this uh, concept here qualitatively mostly, and no numerical thing has been done so far, and also we haven't done any involvement of the physics also. So qualitatively we try to understand the working of the MOSFET here, the depletion type of MOSFET. So you can go through this, okay, and if some discrepancy or differences in concept comes into picture, then we can discuss it about in the next lecture. But you have to put it in front of me before the start of the lecture so that we can have a